Hello and welcome to another video. In this video we're going to be working on find median from data stream. So the median is the middle value in an ordered list. If the size is even, there is no middle value, and the median is the mean of the two middle values. So for like 2, 3, 4, the median is 3. For 2, 3, the median is 2.5, right? So it's either the middle value if it's odd or the mean of the two middle values if it's even. And we want to initialize this class where we have a median finder object and we add integers from the data stream to the data structure, and we can get the median, which will give us the median of all the elements so far. Answers within 10 to the -5 of the answer will be accepted. So let's kind of walk through this example. So we initialize a median finder, we add number. So we add a 1, then we add a 2, then we find median, which should be 1.5, and that's what it is. Then we add 3, and we find median again, and that should be 2, and that is correct. So essentially, we want to be adding numbers, and we want to getting the median pretty quickly. And the problem with doing this with a list, let's say, is if in order to get the median in a list quickly, it has to be a sorted list, right? You have to be able to get the middle value by like the index really quickly. And the problem is if you have a list of a bunch of numbers and you add a new number, the time it takes to insert a number, even into a sorted list, is actually O of n, because even though you can find a location quickly, if you insert into the middle of a list, you still have to move the rest of the numbers, right? And so you'd have to move them, and that would be O of n. So inserting into the middle of a list is O of n. So we need to find like a better way of doing this. And there's a few ways of doing this, but essentially what we're going to actually use is we're going to use heaps for this. And let me kind of explain the thought process for it. So essentially we're going to have two heaps, right? We're going to have a max heap and a min heap. So we'll have a max heap and a min heap. And our goal will be for the number of numbers in each of these to be either the same or the max heap will have one more number, right? So, and basically what we want ideally is we want every number in the max heap to be smaller than every number in the min heap. So if we have, let's say we have numbers 1, 2, 3, 4, 5, in the max heap, we're going to want to have 3 numbers, right? So we'll have 1, 2, 3 in the max heap. And in the min heap, we'll have 4, 5. And then we can easily say like, okay, well, if the lengths are the same, then give me the max number of the max heap and the min number of the min heap, and that's going to be the median. Or if the max heap has more numbers, then the biggest number in the max heap, which is just like the front number, is going to be the median. And the nice thing about this is we're just going to maintain these, and to insert a number is going to be really easy. Like let's say we have this so far. And let's say we try to insert a number, right? Let's say we insert like 15. So what we're going to do is we're going to try to insert 15. And basically, we're going to just try to figure out like where do we want to insert it. And we easily can know that from the min heap and the max heap. We can just say like, look, let's just get the, first of all, let's just say like if they're empty, let's just insert it into the max heap. But if they're not empty, what we can do is we can just figure out like where should the 15 go. And we can just get the biggest element in the max heap, which will be a 3, and we'll say, okay, well, if 15 is smaller or equal to it, then we'll insert into the max heap. And if it's greater, then it should go into the min heap, because every number in the min heap should be greater than every number in the max heap. And the reason we want to do a max heap here is because that way we can get the biggest number in the max heap fast, and we could figure out, like, okay, if our number is bigger than that, we put it into the min heap, and if not, we'll put it into the max heap. So what would happen here is we check, okay, well, 15 is greater than 3, so we'll put it into the max heap. Right? And let's just say we try to insert some more numbers. Let's say we try to insert like, I don't know, 9. Then if we try to insert 9, then what's going to happen here is we're just going to say like, okay, well, if we try to insert 9, where should it go? Well, it should be going into this one because it's greater than 3. So we're going to insert into here, 15, 9, and then so on. And then eventually, basically, all we need to do is do like our little rebalancing, right? And that's going to be pretty straightforward. So all we have to do is we're gonna have two conditions. We're gonna say if the max heap is greater, or if the min heap is greater than the max heap, right? This is the max heap. This is the min heap. Ideally, we want our max heap to have more elements. So we'll just say if this one is greater than the other one, we'll just pop and push. And what ideally would we want to pop and push? Well, we want to take the min number from this min heap and just push it to the max heap. And that's pretty easy, right? Because you can just get the min number by doing a heap pop from a min heap pretty fast. So we're just going to take this 4, push it over here, essentially, and that's pretty straightforward. And then what's going to happen here is we'll have a 4 in here. So we'll have a 4 in here, and now it's the same. And vice versa, let's say we add another number over here. Let's say we add like -5. So the -5 will go in here because it's smaller than 4. So we'll add -5, and then we're going to say, okay, now the min heap. So we want the min heap to either be the same or one bigger, or this max heap, sorry. We want the left max heap to be the same or one bigger than the min heap. Well, now it's 2 bigger, and that's a problem. So we're going to do the same thing. We'll just say, okay, well, let's just take the biggest element in this max heap, and let's push it to the min heap, which will be the 4. So we'll put the 4 over here, which is fine as well, right? Pretty straightforward. So that's how we're going to keep them the same. And then to get the median is going to be really easy. We can just get the max of the max heap and the min of the min heap if they are the same length and get a mean, or if the max heap is bigger, then we can just get the top of the max heap. And then so that's how we're going to do it with 2 heaps. And honestly, the hardest part of this problem is just figuring out on LeetCode how to actually have a min heap and a max heap that actually work. And so I was able to do that. So let me share that. So let's actually code it up. So basically the problem with this is we're going to use priority queues. And the problem with this is LeetCode has like an outdated priority queue from a GitHub repository that I'll link as well in the description. And so you kind of have to know like what's the format for it. So I'll show you for it. But basically the updated one is a lot easier to use, and I will also link the updated code as well. So that way you could see like what, if you were actually coding this, not on LeetCode and like VS Code or something, you could see what that's going to look like. And you can also see how to actually use a heap in LeetCode. So essentially, LeetCode, you can have a min priority queue and a max priority queue. I don't think it actually has a built-in heap. But a priority queue is going to be very similar to a heap. It uses a heap under the hood, so we're going to use that. So we're going to have a min heap and a max heap. So I'll just call this like min queue. And it's going to be type of min priority queue. And we're going to have a max queue, and it's going to be type of max priority queue. Make sure it's spelled correctly. You can also just omit the types. That would also work. So you can just say min heap, max heap. So essentially, the way to initialize this is like this. So you say this dot min queue equals new priority, or it's actually going to be min priority. I want to make sure I spell it right. And even though this is in red, this still works, which is also kind of annoying on LeetCode. So essentially what it takes is it takes an object with a compare function. I think you can give it other things, but essentially you want to give it a compare function. And so the newer one that is not on LeetCode but that you can just download, if you have like numbers or strings, you don't need to give it a compare function. But if you're comparing like objects or something that you're storing in your min heap, then you need to give it a compare function, kind of like you would to a sort. So our compare function is just going to be key compare, and the value will be something that takes A and B. And for a min, this would want to be like increasing, right? So for a min, we'd want to have A minus B, just like a sort. And similarly, for the max, it's going to be almost the same thing, except this compare function will just be the other way around. So we'll have a max priority queue. And like I said, the hardest part of this problem, honestly, is just figuring out how this stuff works in LeetCode, which is kind of annoying. Otherwise, you have to write up your own heap, and writing up your own heap is like a medium to hard problem, so I wouldn't really recommend that. I'd just stick with this. So we gave it a compare function, so now we have a min heap and a max heap. I think it also does have like a normal priority queue, not a min or a max. But yeah, this is how this one works. And then, okay. And like I said, there might be some like easier ways to do this. I haven't used them too much in TypeScript because I'm more focusing on like how to answer the question, and this is outdated anyway. Like now in a max priority queue, if you compare numbers, it knows that it wants the biggest number, so you don't need to give it this compare. This is like this doesn't really make sense for numbers, right? Because like you should know for a max priority queue the bigger number is correct. But regardless, so that's how you do that. So now we want to actually write our add num function. So for the add, what we're going to do is we're going to check if the max heap is empty. So if the max heap is empty, that means the min heap is also empty. So we'll add to the max heap. So if this .maxq.size is the way to get the actual length of it, equals 0, or the number should just go into the max heap because it's in that range, right? So if number is less than or equal to this .maxq.front, so then we will want to add it to the max heap. Q number. Otherwise, we're going to want to add it to the min heap. So this dot minq.nq. And basically nq is like a heap push. So this is just the format for a heap push. Front gives you the min or the max of whatever heap you're in. So the front of a max heap is going to give you the biggest number. The front of a min heap is going to give you the smallest number. And so as an example, let's say we have like 1, 5 as our left heap, and then we have like 6, 7 as a right heap, and we're trying to put in 2. We're just saying, okay, if this heap is empty, or if 2 is smaller than the biggest element in here, then it needs to go in here. Otherwise, it needs to go in here. And then finally, when we do that, we need to rebalance our heaps to make sure that the left heap is actually bigger or equal to the right heap, right? The max heap is bigger or equal to the min heap. So that's what we're going to do next. So we're going to say if this dot max q dot size minus this dot min q dot size equals 2, right? So if the max heap is 1 greater, that's fine, but if it's 2 greater, then that's a problem. And it's never going to be more than 2 greater because it's going to be balanced to begin with. So this can either be like equal elements, right? Like 2 and 2, and then it'll go 3 and 2, or it can start like this, where this has 3 elements, this has 2, and now this will have 4 and this will have 2. So because to begin with, they're balanced already every time we do an add. So if this is 2, then we want to rebalance. So we can say this dot minq dot nq, and then we want to deq from the max heap, right? So we're saying deq from the max heap, which is a heap pop. If you do like Python or something, or just a normal heap. So essentially we're popping from the max heap, and we are pushing to the min heap, and now they will be equal size, right? So if you have like 4, 2, you will take an element from here, add it to here, and they'll be 3, 3 now. Otherwise, we'll have one more check. So also, if the min heap is bigger than the max heap, and it can only be 1 bigger, then we need to do the same thing. So this dot minq is basically the other way now. It's greater than this dot max q dot size. Then we're essentially doing the other way, so we can just copy this and just change the names. So this is max, and this is min. So now they're going to be balanced, where they're either going to have equal length or the max heap will be bigger, and now we can easily handle the median, so we are going to have 2 cases. One, they are the same size, so this dot minq dot size equals this dot max q dot size. So if they are exactly the same, then what we're going to want to do is we're going to want to, like if you think about it, if we have like something like this, and then we have whatever here, if they are the same length, then essentially we want to take the biggest number in the max and the smallest number in the min and get the average. So let's do that. And the way to get like the actual smallest and biggest is use front, right? So we want to return this dot minq dot front plus this dot max q dot front. That'll give us our 2 values. Then we just get the average. So return there. And otherwise, if the other case is our max heap is bigger, and if our max heap is bigger, we just want the biggest number of the max heap. That's guaranteed to be the median. So then we just do this dot max q dot front. And let's try that. See if we get any errors. Hopefully not. Looks like we didn't. Looks like we did. Runtime error. This dot minq is not a function. So let's see, else if, all right, here. Yeah, so we need to do the size. There we go. So let's just go back to this. This dot minq, oh, I misspelled dq. Yeah, definitely hard to spell these. Okay. Hopefully that's correct. Hard to spell q. Okay, there we go. And we'll submit. And you can see it's pretty efficient. So let's go through the time and space for each of these functions. So let's get some more space here. So put it in here. And space. Okay. So for the constructor, obviously it's going to be O of 1. For the add, so essentially what we are doing is we are adding a number to one of them, and we might do like 1 dq, right? So essentially we have a constant time, like constant number of nqs and dqs, you know, anywhere from like 1 to a few, like 2 or 3, and each nq and dq takes log n where n is the number of numbers that are in here. And so technically log n would be, yeah, I guess it would be log n, because it would be the total numbers that you have so far, because ideally you would split your numbers in 2, right? So the length of every heap would be n over 2, which would still be log n. So time for add is going to be log n, depending on how many numbers we have in here total, basically. And find median is O of 1. Because front just gives you like the minimum or the maximum, and right to just peek or whatever thing you're using in a heap to get the smallest element in the mean heap or get the biggest element in the max heap is O of 1, because the heap is basically an array under the hood. So you know exactly where the biggest and smallest value are. They should just be at the first index in that array. So that's O of 1. And as far as the space, so we are maintaining these heaps. And so these heaps are going to be O of n, because essentially we are storing all our data in these heaps. And altogether it's going to be O of n, and you just have half your data in one of them, half your data in the other one. Yeah, and as far as like all the rest of this stuff, yeah. So basically our space for our whole like class is O of n, where n is the number of elements we've looked at so far. But yeah, I think that's going to be all for this one. So hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.